Good day. It's good to be with you today to talk about the length of a curve, arc length, and curvature. It is a little bit of a difficult day for me because my Mariners just lost a marathon 18 inning game, 1-0. I know for you baseball fans out there, that's a big deal. For those of you that don't follow baseball, you can just mourn with those who mourn. So anyway, I guess I'll try to drown my sorrows in calculus. Arc length and curvature. The length of a curve. We define the length of a parametric curve in two dimensions as L equal to the definite integral from alpha to beta of the square root of the quantity dx dt quantity squared plus dy dt quantity squared and of root dt, provided that the various functions and parameters are all well behaved. The arc length in three dimensions is similarly defined. Suppose that r of t equals f of t, comma g of t, comma h of t on a less than or equal to t, less than or equal to b, where f prime, g prime, and h prime are continuous. If the curve is traveled exactly once as t increases from a to b, then the length of the curve is equal to the definite integral from a to b of the square root of f prime squared plus g prime squared plus h prime squared dt, or the integral from a to b of the square root of dx dt squared plus dy dt squared plus dz dt squared, all dt. Notice here that we can also write L as the integral from a to b of the absolute value of r prime of t dt. And this is because this absolute value of r prime of t is the same thing as this integrand, this root up above. Example 1. A glider is soaring along the helix r of t equal to 3 sine ti plus 3 cosine tj plus 4tk. How long is the glider's path from t equals 0 to t equals 2 pi? So to solve this, we need to find the length of the curve. So we need L. And we, of course, remember that L is equal to the integral, in this case, of the integral from 0 to 2 pi of the magnitude of r prime of t dt, where our r of t is the function above. So to find this, it looks like first thing we've got to find is r prime of t. So r prime of t will be 3 cosine t, comma, negative 3 sine t, comma, 4, which tells us that 2, we can find the magnitude of r prime of t, and that's going to be the square root of 9 cosine squared t plus 9 sine squared t plus 16. Notice that there is a cosine squared plus a sine squared, so you could factor out a 9, leaving you 9 times cosine squared plus sine squared, which is of course 1. And so this will be equal to the square root of 9 plus 16, or 25, which is a funny way of writing 5. So first we found r prime, then we found the magnitude of r prime, which is constant, and finally we can find the integral. So L is going to equal the integral from 0 to 2 pi of 5 dt, which will be 2 pi times 5, or 10 pi. So how long is the glider's path from t equals 0 to t equals 2 pi? The length of the path is 10 pi. So let's just take a sneak peek at this particular curve to try to get a sense for the animation, from the animation of what's going on. So again, this curve is a helix. So our glider is going to be spiraling up, and you can see the spiral happening there. And so in our case, we want to know what's the length of the curve from 0, and then we're going to make a full revolution, and right where it ends. And we're saying from t equals 0 all the way to t equals 2 pi, that the glider has traveled a length of 10 pi. So the previous section was about length. This next section is about arc length. So the length of a curve is a constant or a number. The arc length is similar, but is a function. So we define the length of the curve, which is the constant, to be the integral from a to b of the absolute value of r prime of t dt. Again, this is a constant. The arc length for us is a function, and it's s of t equal to the integral from a to t, notice the t in the upper limit, of the absolute value of r prime of u du. Once again, this is a function. You'll notice that we have the dummy variable u. Dummy variable u, since we have that t inside our upper limit, making this as a function of t. So just to repeat again, that in this particular part of the class, this particular part of calculus, when you see s is virtually always going to represent the arc length or the arc length function. Notice here that ds dt equals the absolute value of r prime of t. That is, if you take the derivative of an integral, you get back that integrand, the thing inside the integral. Curvature. A parameterization r of t is called smooth on an interval I if r prime of t is continuous and non-zero on I. A curve is called smooth if it has a smooth parameterization. A smooth curve has no sharp corners or cusps. When the tangent vector turns, it does so continuously. The key thing I'm trying to draw out here is this idea of the tangent vector, and I'm talking about how does the tangent vector change. So if C is a smooth curve defined by the vector function r of t, recall that the unit tangent vector, big T of t, is given by big T of t equal to r prime of t divided by the magnitude of r prime of t. Remember, this formula here is one that you should have memorized. So you should memorize that. And then you might recognize this denominator from what we just learned. That denominator is our s prime of t. So that's our arc length function sitting there inside the unit tangent vector. In the picture, you can see that t of t changes directions very slowly when C is fairly straight. So C is fairly straight in these sections and those sections. Right, so C is fairly straight, and so those unit tangent vectors t seem like they're all going kind of sort of the same direction. There's kind of a similarity. But it changes direction more quickly when C bends or twists sharply. So C bends or twists sharply. That would be in this center section. And take a look at how those tangents change in that region. So you go from straight up, or from horizontal to almost vertical, seemingly very quickly. Okay, so in this section, the fast change in our unit tangent vector. So the curvature, kappa, at a given point is a measure of how quickly the curve changes direction at a point. So it's a measure of how quickly the curve changes. So we're talking about change. Let's see if I can get some color in here. You'd have um, how fast the curve changes direction. So that would be change in the direction of the tangent line. But we want to do this with respect to where we are on the curve. Where we are on the curve would be given by the ds, because that's according to the arc length. So how fast is it changing, dt, with respect to where you are on the curve, ds. And that's our first definition of a new term called curvature. What I want to look at in this picture is how the tangent curve changes direction as we move along the curve with that delta s. And so we can move along the curve and notice that in this region here, the curve is relatively flat, like relatively straight. And so since the curve is relatively straight, our curvature is relatively small. But if we come in here to the sharp part of the curve, notice that right here in this big turn, you have lots of change happening relatively rapidly, and so that curvature is starting to increase. It should be relatively obvious that if your delta s, if the 2 points we're looking at get smaller, then the approximation that we're looking at here that for the change in t will get better and better and closer to the derivative that we're actually talking about. But again, the point of all this in this example is that you get greater curvature when you have a sharper bend, less curvature when the curve is flat. While possible, it is a nuisance to find the change of the tangent function with respect to the arc length, right? That's just difficult. So this definition 1 is kind of hard to work with. But notice that with the chain rule, we can look at that ds, dt ds, that's right here. And we can do a chain rule with ds dt. And dt ds times ds dt will just give us dt dt. That's the derivative of the unit tangent with respect to time. This is a much friendlier looking critter. So we can solve for the unhappy one, dt ds, and find that dt ds equals dt dt, note where that numerator will be big T prime, divided by ds dt, which is the magnitude of r prime. So this gives us a nice friendly formula for kappa, or the curvature. The curvature kappa is the absolute value of, or I should say the magnitude, not the absolute value. The absolute value, sorry, I said it again. K, or the curvature, is equal to the magnitude of big T prime divided by r prime. And this right here is a much more useful definition. It's more useful than definition number 1. Let's look at a second animation to try to help ourselves gain more intuition of this idea of curvature. Okay, here we have a more streamlined picture. And again, what I want you to see is the red unit tangent vector in the left graph. And notice that when the red curve is going relatively straight, that the curvature over here on the blue graph is relatively low. But when we get to the super curvy parts of the graph, right near that vertex, that's where we'll have a lot of curvature. That's where our curvature is highest. And then when the graph gets straight again, the curvature seems to go back down to 0. So big curvature means tight turn, small curvature means relatively flat. So example 2, find the curvature of a circle with radius a centered at the origin on the xy plane. This is kind of a classic question and important. We'll use this result later on. but it also gives you a sense for what's going on with curvature. So let's start by drawing a picture. So if we have a circle on the xy plane with radius a, and we're going to try to find the curvature of this. So we need to parameterize with some r of t. And so we can parameterize this with a cosine t, comma a sine t. And we could add a comma 0 if we were so inclined, but it's actually not necessary for this particular derivation. So once we have r of t, our goal is to find the kappa curvature, which is the magnitude of t prime of t divided by r prime of t. Well, whether we need t prime or r prime, we're gonna have to start by finding r prime. So first, we'll find r prime of t. I should say first we parameterized. So we parameterized before anything. So now we're trying to find r prime of t. So r prime of t will be negative a sine t, comma a cosine t, and we know that the magnitude of r prime of t will equal the square root of a squared sine squared t plus a squared cosine squared t, which once again you can see the common factor of a squared, leaving behind a sine squared plus cosine squared, which is 1. And so all this garbage is going to be equal to a. Actually, it's the absolute value of a, but since a is the radius of the circle, we know that a is non-negative, and so we can ignore the absolute value here. So we have I think I'm missing an absolute value there. R prime. Okay, so now that we have r prime and the magnitude of r prime, this means that we can find t of t. So t of t will be r prime of t divided by the magnitude of r prime of t, which will be negative a sine t, comma a cosine t, all over a. So it's 1 over a times a sine t negative a cosine t, and the a's of course will cancel, leaving you with the t of t is equal to negative sine t, comma cosine t. All right, so we have t of t, which means we can find t prime of t. T prime of t. T prime of t is going to be negative cosine t, comma negative sine t. And we have magnitude of r prime of t. So this tells us, it looks like we ran out of space. This tells us that actually I think I can, let me insert space here. No, I don't know if that works. Okay, so this tells me that kappa, which is the magnitude of t prime of t divided by r prime of t, is the magnitude of the vector minus cosine t over a and minus sine t over A, which would be the square root of cosine squared t over A plus sine squared t over A. Sorry, both of those a's are squared, which will be 1 over A. And so our curvature of a circle with radius A is 1 over A. What this means is, that big circle means small curvature. Small circle means big curvature. Because they're inversely proportional to each other. Although the previous formulas worked for finding the curvature, the following formula is more convenient to apply. So the curvature as a function of t is equal to the magnitude of r prime of t cross r double prime of t all over the magnitude of r prime of t cubed. And this is our third curvature definition. This definition right here is the most commonly used. This is the one you want to memorize. So memorize this one. Note that this formula is not intuitive, and its derivation requires the use of the product rule, the fact that t cross t equals 0, and 3, knowing that if the magnitude of t equals 1, because it's a unit vector, this implies that t dot t prime is 0, or that is, they are perpendicular vectors. The full derivation is in the text. Example 3, find the curvature of a straight line parameterized by r of t equal to the constant c plus tv. Before we get too carried away, let's just think about what these things mean. So we're looking for the curvature, how bendy is a straight line. So we might think to ourselves, gee, that's probably 0. So let's just sort of try to understand why that would be the case. So in order to use the formula that we were just looking at, we're going to need to find r prime of t. We're going to need r double prime of t. And then we're also going to need the magnitude of r prime of t. And we'll need some cross products and other things along the way. So this is what we need. So r prime of t would be the derivative of a constant is 0 plus t times v. So this will just be, v is a direction vector. So maybe like t times the vector 1, 2, 3. And so this is just going to be the vector v. Notice that this is a constant. It's a constant vector because we're on a straight line. Since a line. So that means that r double prime of t, my double primes are a little blurry there. R double prime of t will be the 0 vector. And at this stage, we sort of kind of want to stop because we notice that r prime cross r double prime is going to be v cross 0, which had better be 0. So that tells us that when we go and we find the curvature, we're going to get the absolute value of the 0 vector from here divided by the absolute value of r prime of t cubed, which is not 0, And certainly the magnitude of 0 divided by the magnitude of not 0 is a very happy 0. So just like we would expect, we showed that a straight line has curvature 0. It's curvature 0. Let's do a more complicated example. In example 4, find the curvature of r of t equal to the vector t squared, comma 2t plus 1, comma e to the t, and we want to find this curvature at the point 0, 1, 1. So again, the first thing we're going to want is r prime of t. So r prime of t is equal to, it looks like 2t, comma 2, comma e to the t. And then from there, we can get that r double prime of t is equal to 2, comma 0, comma e to the t. Now, once we've found all of our derivatives, we can evaluate these functions and get to a constant vector or constant vectors. So this is kind of a sticky point for students. So all derivatives are taken. Now we can evaluate. And you might say, what do you mean by evaluate? Well, what I want to point out is that we are at the point 0, 1, 1. And in order to be at the point 0, 1, 1, we could ask ourselves, what time is it? So 0, 1, 1, well, that would require that t equals 0 because of the t squared. So t squared equals 0, so t must be 0. We could check. 2 times 0 plus 1 is 1. That worked. E to the 0 is 1. That worked. So our time equals 0. You'll never want to take derivatives, or sorry, you'll never want to evaluate until after all of your derivatives are taken. This is, again, this trips students up pretty regularly. But anyway, so now we can do part 1. Maybe I'll call it like 1 star because we're kind of coming back to 1. So r prime of 0, because it's t equals 0, will be the vector 0, 2, e to the 0 is 1. And step 2 star, because we're coming back to 2, will be r double prime of 0. And that's going to equal 2, comma 0, comma e to the 0 is again 1. Once we found our r prime and our r double prime and evaluated them at 0, we can continue on step 3 and find r prime of 0 cross r double prime of 0. And since we already have the vectors written, we can just write our cross product down below them, sort of visualizing the ijk above, but without writing it. And so it looks like our I component is going to be 2 times 1 minus 0, or 2. Our j component, remember the negative that's built into the formula. So our j component is going to be 0 minus 2. And our k component is going to be 0 minus 4. So it looks like we have 2, 2, negative 4. One thing I like to do when I find my cross products is to quickly check them against the original vectors. So check, one color, arc. Check with the dot product. So if I want to check with the dot product, like I'd be taking this yellow vector and dotting it with the other yellow vector. So 0 times 2 plus 2 times 2 times 1 times negative 4. Yep, that equals 0. And then I'd be taking the blue vector and dotting it with the blue vector. 2 times 2 is 4, plus 0 times 2 is still 4, plus 1 times negative 4 is 0. So yep, we did our cross product correctly. We found a perpendicular vector. Okay, so we have r prime of 0, we have r double prime of 0, we have r prime of 0 cross r double prime of 0. Now we need some magnitudes. So we need, maybe this is 3 star. So we need the magnitude of r prime of 0 cross r double prime of 0. So this will be equal to the square root of, looks like 2 squared, which is 4, plus 2 squared, which is 4, plus negative 4 squared, which is 16. And all this stuff is a funny way of writing square root of 24. And then we also need to work with our r prime. So maybe we'll call this, since we're going back to our r prime of 0, maybe we'll call this 1 star star. And we need to find the absolute value of r prime of 0. And this will be equal to the square root of, it's like we have 0 plus 4 plus 1, which is a funny way of writing square root of 5. And so when we put all this stuff together, our curvature, here's our conclusion. Conclusion is that k, or the curvature, is going to be the square root of 24 divided by the square root of 5 cubed. And again, that square root of 24 came from here. The square root of 5 came from there. And the cube, the whole thing came from the formula. So there you have it, the curvature of this curve at the point 0, 1, 1. The normal and binormal vectors. At a given point on a smooth space curve R of t, there are many vectors that are orthogonal to the unit tangent vector t of t. We want to show that t prime of t is one of them. So we're going to do this in 2 steps. The first step requires that we remember that t is a unit tangent vector. That is, it has a length of 1. So step 1, we're going to look at t of t dotted with itself. You may remember that t of t dotted with itself is equal to the magnitude of t of t squared, which, since t of t is a unit vector, is equal to 1. So the second thing we're going to do is we're going to differentiate both sides of this equation, that t dot t equals 1. So when we differentiate both sides, we get that d dt of 1 to 0 is equal to d dt of t dot t of t. And here we get to use the product rule for dot products. And so this will be t prime of t dotted with t of t plus t of t dotted with t prime of t. And we notice that the order doesn't matter with the dot product. So these 2 terms are the same, this implies we have 0 is equal to 2 times t of t dotted with t prime of t. Obviously, the 2 isn't doing anything here, so we know that 0 is equal to t dot t prime. Therefore, we can draw the nice conclusion. The 3 dots means therefore that t is perpendicular to t prime. Just like we set up here. T prime is orthogonal. T prime is orthogonal to t. Historical note. The mathematicians Frenet and Siré independently discovered and described the kinematic properties of a particle moving along a curve using the tangent, normal, and binormal vectors. However, our modern notation for vectors in linear algebra did not exist for them. So today, their formulas are called the Frenet-Siré formulas and relate what we now call the TNB frame with the curvature K and the torsion T. This next page includes a fairly long derivation. So since t prime of t is not generally a unit vector, we will define the principal unit normal vector, n of t, or simply the unit normal, as n of t equal to t prime of t over the magnitude of t prime. Notice that t gives the direction of motion and n points in the direction of the curve is turning. We call the vector b, which is t cross n, call this the binormal vector, and it is perpendicular to t and n. So in this animation, you get a sense for the tangent, the normal, and the binormal vectors. So notice these are living in 3 dimensions. You can see from the animation that t, n, and b are all perpendicular to each other. They're all unit vectors living in the same, kind of in the same space. You'll notice that notice here how the curve is sort of curving here to the left, and that normal vector is pointing into the direction of the curve. And the binormal vector is perpendicular to the t and the n vectors. Notice as the curve out here, the curve is pointing kind of downwards, the n is pointing towards us, but as we reach kind of this place where the curve starts to change, notice what's happening, that our blue normal vector is starting to point up, is starting to rotate, and then pretty soon it's pointing into here, it's pointing into that curve for the remainder of the distance traveled. So you have, again, the tangent vector is pointing along the curve in the direction of travel. The normal vector is pointing in the direction of the curve, and the binormal is perpendicular to both t and n. And all 3 of these are unit vectors. So this is actually our first example of an interesting but different orthonormal basis. It also gives us what we call the TNB frame, or like the TNB reference frame. The plane determined by the normal and binormal vectors n and b at point P on a curve C is called the normal plane of C at P. So this is the plane formed by the normal and the binormal. So the normal and the binormal, that would be this plane here. It consists of all the lines that are orthogonal to the tangent vector t. And here's that tangent vector t. The plane determined by the vectors t and n is called the osculating plane of C at P. The name comes from the Latin osculum, meaning kiss. It is the plane that comes closest to containing the part of the curve near P. And so this is containing T and N. That would be this plane there. And there's a third plane, the rectifying plane, formed by T and B. Let's look at another animation. But here's that same animation with the T, N, and B that we had earlier. And here we want to point out the normal plane. And you'll notice that the normal plane includes those N and B vectors and is perpendicular to the curve. So it's like the curve is always skewering exactly straight through the normal plane. And then the osculating plane is always sort of perfectly in line with the direction of travel. So maybe if you thought about the T is like the nose of an airplane and the N is one of the wings of the airplane. So that osculating plane is sort of like literally a plane formed along a plane, where you've got a plane flying along a curve. You can think about that osculating plane as being kind of like right through the middle of the plane. Here we do a little barrel roll, and then for the rest of the time, everything again seems to look pretty good. So it's just that motion of a plane. So there's your osculating plane and your normal plane. Putting this in a static environment, you can again think about that TNB frame as being the tangent vector, think with your pointer finger, the normal vector with your middle finger, and your thumb being your binormal. And so you're kind of imagine flying along the curve. Right. And as you travel along the curve, your pointer finger is always pointing in the direction of that tangent vector. There's an example there, like with a helix. And so as you travel around, your pointer finger is always pointing into the center of the helix. The thumb's always pointing up, pointer finger kind of in the direction of travel. Or we have here on the right, we have here on the right, you can see this curve showing up. And you can see again, the motion of travel going in the T direction, N pointing in the direction of the curve, since the curve seems to be going up. So the N would be pointing kind of into your finger, and then the binormal is kind of pointing out towards us in space. So T and B, tangent vector, normal vector, binormal vector. Maybe more specifically, you could think about this as the unit tangent, the unit normal, and then the binormal vector is a unit vector because it's the cross product of two perpendicular unit vectors. Note, for a plane curve, the osculating plane is simply the plane that contains the curve. Remember, a plane curve here is one that lives in 2 dimensions. Now, it doesn't necessarily have to be just in a 2-dimensional world. It could be a plane that lives in 3 space, but have a line that's drawn on top of that plane, for example. So it's just a 2-dimensional curve, possibly living within a 3 or more dimensional space. The circle that lies in the osculating plane of C at P has the same tangent as C at P and lies on the concave side of C, towards which N points, and has a radius of rho equals 1 over kappa. And it is called, that's a typo, it should be called, it is called the osculating circle of C at P. It is the circle that best describes how C behaves near P. It shares the same tangent, normal, and curvature at P. So osculating circle is this circle right here. And you'll notice that it's at the point P. It shares the same tangent, T, and it shares the same normal. Need another color. Shares the same normal n, and the radius is going to be rho equals 1 over kappa. Let's give a non-technical description. So imagine a car moving along a curved road. So here we are moving along our curved road. Okay, on a vast flat plane. Suddenly at one point along the road, the steering wheel locks in its present position. So it's a curved road, you lock, so you sort of keep that same turning position with the steering wheel. The curvature of the circle is equal to that of the road at that point. So the circle, you can imagine if the steering wheel locks, then you're just going to keep driving in a circle, right? But for a split second, are you on the road or are you on the circle? The curvature of the circle is equal to that of the road at that point. The circle is the osculating circle of the road curve at that point. Let's look at another manipulate. So here's what I want to point out to you in this particular drawing. So notice that right in this region, notice that the point in on the curve and the circle are the same. And notice that the circle is almost like a tangent circle, right? They share the same tangent line. So our tangent line appears to be the same in both cases. This isn't perfect, but gets the idea. So the tangents are the same, but they also have the same amount of curviness right at that point. As our point moves along, notice that when the curve is really tight, like kind of like at a tight part of the curve, that the circle is smaller. When we're at a flatter part of the curve, the circle is much bigger. But in each case, they have the same normal, kind of pointing towards the center. They have the same tangent, but they also have the same curvature. Okay. Watch what happens as we go from this concave up part of the black curve to the concave down part. So notice that the circle is getting larger and larger and larger and larger and larger. And it's above the curve, so the curvature is above. And then right when we hit that point of inflection coming up, what's going to happen? Right at that point of inflection, boom. Oh, I passed it. Notice the normal is pointing in because it's a giant circle pointing towards the kind of up. And then boom, one click later, it's a giant circle pointing pointing down. And you can see, once again, you'll get that curvature. Once the curve gets tight, you'll end up with a small circle, then it gets big again. The radius of this circle is the inverse of the curvature of the curve at that point. So bigger curvature will make smaller radius. Smaller curvature will make bigger radius. Example 5, consider the space curve r of t equal to 3 sine ti plus 3 cosine tj plus 4 tk. And this is, I believe, the same example that we had earlier on in the section. Let's look at a picture to try to understand what this looks like. So first of all, this is a helix. The shape is a helix. And so your r of t is drawing out that spiral that we've seen multiple times in this class so far. There's that helix being created by the r of t. Okay. Our unit tangent, I'm trying to figure out which of these pictures I want. I don't want ut and t in the curve. How about this one? So you can think about the tangent like it's like the paper airplane that's tracing out that path. So the helix is the path left behind that paper airplane. So that's our unit tangent vector. Our unit normal vector is going to point into the direction of travel. So notice it's always pointing kind of like into the curve. You're always looking for where is the curve happening. Wherever that curve is happening, your normal vector is always pointing into that curve. And then lastly, well, not quite lastly, you have the normal vector, or sorry, the binomial vector doing the same thing, but it's pointing perpendicular. So as we wind our way around, the binomial vector is always pointing up as we spiral around our helix. Where this gets really cool is when we add that osculating circle in. So here's that osculating circle. You can see that that osculating circle is right on the plane formed by the green and the red vectors. And if I get rid of the Tn and B, notice, I just think this is so cool. It's like you can't even tell where the curve and the circle meet. They sort of like are one right on top of the other, because the curve is so perfectly in tune with the osculating circle, or maybe that's vice versa. Let me look at another example of the same thing. Here's a trefoil knot, slightly more interesting curve. Let's see if this will work. So here's that trefoil knot shape. Kind of a funky little knot shape. And if we look at the osculating circle and the curve, notice again, you can't even tell where the curve ends and the circle begins. But they sort of like seamlessly work together. The circle seems to flip over whenever that normal curve, like when the curve goes from pointing one direction to pointing the other direction. It's your osculating circle. Yeah, so to me that osculating circle is one of the most beautiful pictures that we have in all of calculus. I just love the way the two of them just work together so unbelievably elegantly. So example 5. Sorry. Consider the space curve r of t equal to 3 sine t, comma 3 cosine t, comma 4t. And this is from example 1. So first we want to find the unit normal vector. I think we found the unit tangent. It's been a while. I don't remember what it was. So let's derive it once again. So we need r prime of t, which will equal, looks like 3 cosine t, 3 negative 3 sine t, and 4. And the magnitude of r prime of t, which will be square root of 3 cosine squared t, 9 cosine squared t, plus 9 sine squared t, plus 16. Factor out the 9. Oh my gosh. Factor out the 9, and you're left with a cosine squared plus sine squared, which is 1. And so this is equal to the square root of 9 plus 16, or 25, which is 5. So we get that 3, the unit tangent is going to be the vector 3/5 cosine t, comma negative 3/5 sine t, comma 4/5, where the numerators are coming from here and the denominator is from the magnitude. So that's our tangent vector. So now we want the unit normal vector. So to find the unit normal vector, we need to find the derivative of t. So we're going to find t prime of t, which is going to be the vector 3/5 sine t, but negative, and negative 3/5 cosine t, and 0. We need, in order to find the unit normal, we need the magnitude of t prime. So 5. We need the magnitude of t prime of t. This will be the square root of, looks like 9/25 sine squared t, 9/25 of cosine squared t, plus 0, all under the radical. Notice again, you have a common factor of 9/25, leaving behind a sine squared plus cosine squared. Ooh, typo here, this is a plus. Leaving behind a sine squared plus cosine squared. So all of this stuff together is the square root of 9/25, which would be 3/5. So putting these things together, we get 6. We get that the unit normal vector n of t is equal to 1/3/5 times the negative 3/5 sine t, negative 3/5 cosine t, comma 0, which is a funny way of writing, like the negative 3/5 and the positive 3/5 are going to cancel out. So this is just negative sine t, comma, negative cosine t, comma 0. We can test this out by, we can check it, I should say. We can check it by looking at t dot n. If we take t dot n, we're going to get, looks like positive 3/5 sine squared plus positive 3/5 cosine squared. Oh, sorry, I'm dotting with the wrong thing. So if I want to check, I'm going to check by looking at the result from n of t and dotting it with the result of t of t. So I'm going to dot these two together. So we dot the two together. It looks like we would get negative 3/5 sine cosine plus positive 3/5 sine cosine plus 0, which is indeed 0. In part B, we're asked to find the binormal vector, but you'll notice something has changed because now we're asked to find the binormal vector at a point. Okay, so this is very important. You cannot evaluate your vector functions until you're done taking derivatives. So in these cases, that means you can't evaluate until after you're done finding your tangent and your normal vectors. But remember, in order to find the binormal vector, we just need to take t and cross it with n. No derivatives involved. So at this stage, we can evaluate. Notice that our curve, you can ask, what's the time when we're at 0, 3, 0? So our curve is here at r equals 3 sine, comma 3 cosine, comma 4t. And so you'll notice that we are going to be at the point 0, 3, 0. Is that a point or a vector? I guess this is a position vector. And this will happen when time equals 0. So again, if you were basically
having to find the time value when we will be at the given point. So, and this isn't that difficult to do. Notice we're given a 0, told the 0 must be equal to 4t. So that's what tells us, the combination thereof is what tells us that t equals 0. We can check by saying if time equals 0, we would get 0 here, and we would get 0 at sign. And at time equals 0, we'd get 3 cosine of 0, or 3, or 3. So we can see that in all three cases, if time is equal to 0, everything is going to match really nicely. All right, back on track. So we know that time equals 0. We're looking for the binormal vector, which is tangent times the normal. And specifically, we're looking for it when time equals 0. Because time equals 0 is what matches the 0, 3, 0. So let's figure out how this works. So our tangent vector at 0 would be 3/5 cosine of 0, or 3/5, comma, sine of 0 will be 0, so I'm going to get a 0. And then I've still got a 4/5 over there. This is from the gray star. And then we're going to cross it with the red star. And it's the red star when time equals 0. So at 0, n of 0 is 0, comma, -1, comma, 0. That's from the red star. So let's cross these things, see what we get. IJK, and we have the gray one, which is 3/5, 0, 4/5, crossed with the red one to 0, -1, 0. And the cross product there will be equal to, looks like, positive 4/5, comma, negative is built into the formula, but I'm going to get a 0, comma, -3/5. For me, I find the cross product like prone to mistakes, so I'm going to check. And I'm going to check with the dot product. So I can start by finding the dot of my gray vector and my cross product vector. So I'd have, it looks like 12/25 plus 0 minus 12/25. That looks like 0, so that one checked out. And then if I checked that cross product vector and the other starting one, I'd have 0 plus 0 plus 0. It looks like that one's 0 as well. So my cross product seems to be at least perpendicular to the two vectors that I started with. So I can conclude that my binormal vector at the point 0, 3, 0, or at time equals 0, is equal to 4/5, comma, 0, comma, -3/5. In part C, we want to find the equation of the normal plane at 0, 3, 0. And so remember that if we want the equation of a normal plane, we're looking for a plane that kind of like the curve is just going to jab right through the middle of the plane. So plane that has normal vector, and the normal vector it has is the unit tangent vector t. In our case, t is going to be 3/5, comma 0, comma 4/5. And those are all positive. And so our normal plane will simply be 3/5 times x minus 0 plus 0 times y minus 3 plus 4/5 times z minus 0 equals 0, where the 3/5, 0, and 4/5 are coming from the unit tangent vector, and the 0, 3, 0 are showing up in the equation here. This could simplify if you wanted to 3/5 x plus 4/5 z equals 0. If we want the equation of the osculating plane at 0, 3, 0, we need to remember that the osculating plane is the plane with normal vector, or with perpendicular vector b. Perpendicular vector b, or the binormal. It's the osculating plane is the one that kind of holds the nose of the plane and the wings of the plane. And so remember that b in our case is equal to 4/5, comma 0, comma negative 3/5. And so our plane for osculating or kissing plane will be 4/5 times x minus 0 plus 0 times y minus 3 plus, minus 3/5 times z minus 0 equals 0. Or if you simplify it, it looks like we have 4/5 x minus 3/5 z equals 0. Let's remind ourselves what the picture looks like here and the picture looked like on the previous question. Here's our animation once again, and remember that t is directing its way along the curve, n points in the direction of the curve, b is perpendicular. So our normal plane is the plane that includes n and b, and so the perpendicular vector to that normal plane is the t vector. That's why we used t in the previous part. So t is sort of jabbing its way through. The osculating plane, on the other hand, includes the n vector and the t vector. Its perpendicular is the binormal vector. And notice again that osculating plane, that's the one that's just sort of includes the wings and the tip of the airplane, if you will. In this last part, we want to find the equation of the osculating circle, again at 0, 3, 0. And here we're going to have to be a little bit clever. So let's do a little bit of review to start with. So if we want to do a little bit of review, imagine that you have a circle that's somewhere else it's not centered at the origin in the xy plane. So it's centered at AB, it's got radius r, okay? Then you could parametrically represent this circle with the equation like r of t equals, looks like we'd have A plus R cosine T and B plus R sine T. And so notice that the AB, which represents the center of the circle, is showing up here. The radius, R, is showing up. And then you have this cosine sine that's giving you the circle. Now we can split this up even a little bit more just to help set the stage for our osculating circle. We could write this as AB plus R times, maybe you could think about it times the vector like cosine T in the I direction, which would be 1, 0, plus sine T in the J direction, which would be 0, 1. Here's our I vector, and here's our J vector. Again, here's the AB, here's the R, and then our sine cosine are showing up, but it's sine and cosine times this IJ, which are forming our standard basis vector. Okay, so let's think about what happens when we work with our kissing circle. Actually, before we get to our kissing circle, let's go look at an animation and try to understand again what's going on with that kissing circle. All right, so here we are back with our trefoil knot, trying to understand the kissing circle. Maybe this is a good spot. Yeah. How about there? Okay, I'm gonna turn on my T, N, and B. So notice, let's go back. Notice that the direction of the kissing circle is given by the red and the green vectors. That's the tangent and the normal vectors. And notice that the center of the circle isn't even actually on the curve. The center of the circle is at whatever that point is, and then we've got to go one radius in the direction of the normal vector. So we got to take the normal vector and follow that normal vector right into this to the center. So maybe let's go back to our work and try to see how that plays out. So first up, we have the shared point. So our shared point is given. That's the point 0, 3, 0, right? Coming from R of T. Okay, that's great. And then, so now that would be like a point on the edge of the circle. So now we've got to find the center of the circle. And to find the center of the circle, we need to do two things. First, we need to know the radius of the circle. Radius rho equal to 1 over the curvature. And then once we have that radius, we can find, we can take our point 0, 3, 0. I guess this is a vector for our purposes. 0, 3, 0. And then we can add to it rho times our normal vector. We can go a radius in the distance of the normal vector. So that will be our center of the circle. So in order to do this, you can probably see we're going to need to have to find our curvature. So let's recall that we had multiple formulas for the curvature, but that curvature K was equal to the magnitude of t prime of t divided by r prime of t. That's like how fast is the unit tangent changing divided by the magnitude of the arc length. And so, and these are both magnitudes. So this would be equal to, that is, I think it's like magnitude of this one divided by magnitude of that one. So t prime of t and r prime of t are both quantities that we found earlier on in our notes. All right, t prime of t magnitude and r prime of t magnitude are both things we can easily find based on other things we found in our notes. And remember, we're trying to evaluate this when time equals 0. So you may recall that t prime of t was equal to, oh my gosh, I think it's like a negative 3/5 sine t comma negative 3/5 cosine t comma 0. And so when I evaluate at time equals 0, this is going to be 0 comma negative 3/5 comma 0. And the magnitude of that is just going to be 3/5. The magnitude of r prime of t is constant for all t, and it was 5. And so that tells us that our curvature is going to be 3/25, which tells us that our radius, rho, is going to be 25/3. So remembering our normal vector, and going back to our question we're working on, this tells us that the center of our circle is going to be at 0, 3, 0 plus 25/3. I'm sorry, this is negative, right? No, 25/3, pardon me, 25/3 times 0, -1, 0. And so the center will be at, it looks like 0, 9/3 minus 25/3, or minus 16/3, comma 0. So that's the center of the circle. So here's your shared point. Here's the center of your circle is at 0, -16/3, comma 0. And so together, those are taking the place of this AB in our formula. Our R, so our AB is going to be that 0, -16/3, comma 0. It's in green. Our R is this 25/3, which is nice. Cosine and sine are going to stay the same. And the only thing that we need to mess with now is our I and our j vectors, because that the I and the j vector would be in terms of the standard basis vectors. We don't want to be in terms of the standard basis vectors. We want to be in terms of the tangent and the normal vectors. And so we're going to replace the first of those with the t vector, and the second of those with the n vector. So all told, our circle, our kissing circle, is going to have parametric equation r of t equal to, let's have the 0, -16/3, comma 0. That's the center of the circle. plus R, which is the 25 over 3. Yeah, 25 over 3. So I get a little excited. So that's that green value. Parenthesis. Now I'm going to get a cosine t, which is built into the formula. And I need to multiply by the t vector, which is 3/5, comma 0, comma 4/5. And then plus sine of t times the gray vector, which is the n vector, which is 0, -1, 0. So make sure you're seeing the vectors. Again, this is the t vector, and this is the n vector. So all told, the parametric equations for your osculating circle or your kissing circle are the center of the circle here, center of the circle, plus the radius of the circle times the quantity, cosine times the tangent vector, plus sine times the normal vector. It ain't easy to find, but the picture makes it worth it. So there you have it. Arc length, curvature, the TNB frame, the osculating circle, all kinds of pretty stuff. I hope that helped. Hope you enjoyed this video, and I look forward to seeing you for the next lesson.